Alrighty, howdy everyone. Hi. We'll get started just so we have the most time to review for tomorrow and Friday. So welcome. Yeah. Happy Halloween too. I brought candy, so after this or in between questions and whatnot, if you feel free to help yourself. Be safe, whatever you do. And then tomorrow we have an exam if you're in Dr. Bengali's class, and then if you're in Dr. Altamos's class, so you have that on Friday. You should have taken your quiz. If you didn't take your quiz, please make sure you reach out to your professor so you get that done. And yeah, one more test and then you just take your final and you're done with this class. Alrighty. Any questions for me? Yeah.
Like polarity and then like the ion, all that stuff.
Yep, absolutely. So when we talk about polarity, what causes polarity? So electronegativity differences. Right, is what's going to cause something to be polar. So when we look at the periodic table, where is the most electronegative element? Fluorine, right? So fluorine is most electronegative. What does it mean to be electronegative? Good, right? Electronegativity is the want of an electron. Like, how badly do you want this? So fluorine is the smallest element on the periodic table that does not have a complete valence shell. So the electrons are close to the nucleus. It's one away from having a full octet. So this really wants the electrons. This is going to be the most electronegative. Where's our least electronegative? Yep, the bottom left, right? Bottom left is least electronegative. Right, and when we think about that, as we go down the periodic table, our atomic radii increases. And so the farther away that electron is from the nucleus, the less of a hold that the protons in that nucleus have on that farther electron. So it's able to give it up, right? If it gets rid of that one electron, then it goes to its full valence shell. So the bottom left, I think it's francium, is the most is the least electronegative atom on the periodic table. So when we have differences in electronegativity, that's what causes something to be polar. So if we have something like carbon and fluorine, you might be given values where the electronegativity of carbon is 2.4 and the electronegativity of fluorine is 4.0. The difference between that, right, 1.6 is going to be like what polarity that bond is going to be. If we have something where we also have a carbon and oxygen bond, and this time the electronegativity of oxygen is 3.6, we see that the difference between carbon and oxygen is going to be smaller than the difference between carbon and fluorine. When we talk about polarity and we say, okay, we know that there's a difference in electronegativity, this bond is going to be polar, what does that create? What do we draw to indicate a polar bond? We draw a dipole. And when we have a dipole, we're going to point towards where the electrons are going to spend more time, right? If the element wants the electron more than the other one, then more of that electron density is going to be around that fluorine or that oxygen molecule. They will be more around the fluorine molecule compared to the oxygen molecule because fluorine's more electronegative than oxygen. So you point the arrow towards where the electrons are going to be, and you create that positive sign. If you drew a circle, it looks like a plus sign, a cation, if you will. And so that's where the positive end is going to be, the electropositive side. Okay, and so this is what causes polarity. Polarity comes into play when you talk about molecule shapes, right? You can have polar bonds and non-polar molecules if they're all symmetrically being assembled around the atom or around that central atom. But you could also have elements that have polar bonds and then still be overall polar as well. And again, this all comes down to the shape of the electron or of the molecule. Yes.
What's the range of these?
Yeah, 0.5 to 2-ish. Really, you're going to say anything is non-polar is going to be a carbon-hydrogen bond. Oops. Carbon-hydrogen bond or something bonded to itself. So oxygen bonded to oxygen, fluorine bonded to fluorine, carbon bonded to carbon, right? Anything where the same element is bonded to itself, that'll be non-polar because there's no difference in electronegativity.
Is that true? Hydrogen bond like it's like C5H10.
Yes, right. So you can say if anything, right, if it's just carbon and hydrogen, that whole molecule is non-polar. It's just the electronegativities of both of them are so similar that they don't have an effect on each other. Yep.
It's like the electronegativity difference, like one or something. Is that what she asked about?
Yep. So if it's like 0.1, then it's nonpolar. It has to be about 0.5 in order for it to be considered polar. Is not polar. Yep. There would still technically be some polarity in there. And so that's why I'm saying, right, nonpolar is just when it's carbon and hydrogen and when it's the same element bonded to itself. Carbon and, or sorry, oxygen and fluorine, they're very close together. Their bond is like 0.4 apart. But that's still going to be difference in polarity. And so you would know that that is still polar. They're going to give you obvious polar and nonpolar elements too. You don't have to. They're gonna give you obvious cases where it's gonna be like carbon and chlorine or carbon and fluorine, something like that. And then the same element bonded to itself or carbon hydrogen. Yeah, they're not trying to trick you there. Any other questions on polarity?
So what if it is like right?
I don't think you're gonna have a case where it's gonna be 0.4. If it is, it'll probably be in a range of where you have to rank the differences in electronegativity. And so that would be your least polar, and then your most polar would be the larger difference. Yes.
So whenever you have lone pairs in the central atom, like,
Mhm.
is that like most of the time mean it's gonna be non-polar, so you pulling the direction?
Most of the time, yes, right? If there is lone pairs on the central atom, I would say probably 9 times out of 10, it's going to be polar, but there are a couple cases where it is not polar.
Usually non. Once they're different.
Yes, if it's a 4 electron domain and it's tetrahedral and it has no lone pairs, then it's usually nonpolar, assuming that everything bonded to the central atom is the same element. Yep. Yep.
So the dielectric you just said, if the arrows were pointing into the central atom, you're saying that would be non-polar?
That would also be nonpolar. Yep, because if we had something, I don't know, we'll say, right, I'm just gonna make it up. Assuming that the atom in the center is more electronegative than the outside atoms, and the electron or the dipoles are pointing in, that's still all going to cancel out because it's like 2 trains running at each other, right? They're all going to converge at that central point and they all cancel out.
It's where it's, if all the arrows are pointing in, it's non-polar, it's that shape.
Yes, right. So you could have carbon, oxygen, right? Those pull out towards the oxygens and those cancel out because it's like tug of war that way. But if they were pushing in, then those would still cancel out.
Okay, so linear.
Yep. You can think of linear as like tug of war, right? So if they're both pulling out and they're equal and opposite in strength, then that central or pouring is not going to move.
But if the arrows are pointing in,
They cancel out as well. Yep.
The arrows can, like, you can have arrows pointing in and out.
Yes.
And not, and be non-polar, and be non-polar.
Yes. Yep.
Okay.
So if right in the case on the left, all of the arrows are pointing in, so they're all going to cancel out when they all hit the center. Same thing if it was linear and they were pointing in, right? It's going to be 2 cars running at each other at the same. They're going to hit in the center and they're going to stop.
So non-polar is where they like are pushing in a slightly, like, a different direction.
Yes. Yep. So a polar case would be if, right, for some reason, right, things are pointing both this way. Now you have one side that's being tugged. And so, right, if you hold it like an arrow or you tug it like a rope, then it will all pull to the right in this case. And that would be a polar molecule. Yep.
One of those had a single bond and the other had a double bond. Would that be non-polar because they're different strengths?
You would have to check to make sure it's not a resonance structure, right? So if we look at something like, I put this in. I put this in my additional practice problems as one of the ones that you could do. Right, you have CO3, 2-. In this case, right, that double bond can move to the other two oxygens that are in this structure, right? So you could have it where it's like this, or you could have it like that. And so the average of all of these is going to be that each one of them looks like 1.3, right? Because you have 4 bonds and 3 locations. So the average is 1.33 bond length. So then they would, since they all look the same, technically, like if we were to consider all of them together, then they would all be the same. And then that was when it would still be nonpolar. If it was something where it was, I don't know, again, I'm just going to use X's and Y's, right? Right, if it's like this, and then that double bonded to the Y, it can no longer make resonance structures, then that's when it would still be polar. Yep.
You get like a
So that would be if you're given something where like that starts off looking like that, right? They would say, draw the structure for CO3 2 minus or NO3 minus, right? Then you know that you have to show the entire brackets because the overall molecule and the overall structure will have a charge to it.
So the shape with the trigonal.
Mhm.
Triangle thingy, the arrows are pointing in. Does that mean that it's polar?
Yes, yep. So that's still gonna make it polar because if we look at something like this shape here, right, whether that's pointing out or pointing in with your dipoles, right, so it can point this way or it can point this way, depending on the strength, right? You can consider everything pulling out, right? If you think of the tripod, right, everything's pulling on the legs of the tripod. So it would move down in that case. Or they're all pushing in towards the center. So it's like pushing up on the tripod and it's gonna all converge in the front. So that lone pair distorts the angles and therefore it's no longer symmetrical.
And with those bone pairs, they're all the same angles.
Yes.
That's why.
Yes, yep,
Maybe there's other angles.
yep. So right, these are now like 107-ish. So this is like 111, whatever, right? So because they're not all the same, they don't have the same angle that they're pulling or pushing towards that central atom, that's gonna cause it to be polar. Yep, yep.
But it has like 2 levels.
Mhm.
What is it?
Yep, so. So when we look at xenon F4, what is the electron domain geometry for this one? Is octahedral. Because how many electron domains are there? 6. 4 from the bonds to fluorine, 2 from the lone pairs. What is the molecular domain geometry? Square planar. Where are the bonds within our octahedral? Are they on the axial or equatorial position? They're all on the equatorial position. Where are our lone pairs? So if we're thinking about a globe, right, in the equator, we have all of our fluorines pulling out at the corners of our entire, right, like pyramid that we're looking at. If you think of just a square, right, they're all pulling at the diagonals. Those lone pairs are sitting axial, so sitting on top and on bottom of that xenon. And so because they're going to be opposite each other, they're going to take up the same amount of space. And that's going to cancel out any like extra space that they're taking out because the fluorines will still sit planar, right? They're sitting plain, flat on the bench top. So that's where there are lone pairs, but the molecule is still nonpolar. Does that make sense? Yep.
Question 19 on the Gauss.
Any other questions on this before we move on? Yeah.
So they're non-polar because they balance.
Yes. Yep. Yeah.
That Lewis structure you drew of the carbon and the reactive, how come you did a double bond instead of just doing a lone pair on carbon?
So if we did this. So if we did this instead, what is the formal charge on all of the oxygens? Does anyone know what the formal charge on oxygen is? So on the one where there's 3 single bonds, -1. What is the formal charge on carbon? What's the formal charge formula? Mm-hmm. Okay, so if we're looking at carbon, we have how many valence electrons for carbon? We have 4. How many dots does it have? 2. How many lines does it have? 3. So what's our formal charge? -1. So that means that all of our atoms in our Lewis structure have a -1 formal charge. What does that add up to for our total charge? 9 is 4. What is the charge on CO3? 2-. What do our formal charges have to do in the very end? They have to add up to the charge of the molecule. So we can't, this is not an acceptable structure because our formal charges do not match the charge of the molecule. So in order to create a formal charge of just -2, we have to create the double bond. Does that make sense?
Did you just put brackets around one of them just to show, or do you only need brackets?
I just showed it as a possible choice, and then I showed the resident structures on the side. Yep. Yeah. The CO3 2-, it would be nonpolar because the average of them is 1.33. So your bonds actually look like, right, 1 1/3. And so they would all look like 1 1/3. So they're all pulling in the same strength. Yep, because it's a resonance structure.
We'll talk about the resonance structures and think about nice word.
Yes.
So why are those things?
So your resonance structure means that double bond is going to move around to all 3 of those spots. So it's not going to look like a double bond and 2 single bonds. It's going to look like an average of the double bond being everywhere at one time. And so therefore that creates an overall sense that the bond length is the same between each molecule. Okay, right, so that like they all look like 1.33, they don't look like 1 and 2. Are we clear on this? Yes? Okay. So let's look at chlorine F3, and we'll do this together. So if we're looking at question 19, right, in the correct Lewis formula for ClF3, how many lone pairs are around the central atom? So how many total valence electrons do we have in this structure? We have 28. What goes in the center? Chlorine. We make 3 bonds to fluorine. How many electrons did we use? Where did those electrons go? Around fluorine. How many electrons did we use here? We used 18. How many do we have left? 4. Can we create double bonds with fluorine? Not really. So where do we put those instead? On the central atom. Can we do that for chlorine? Why? It's in the 3rd period, right? So in the 3rd period, you now have that D subshell that you're able to expand your octet into. and chlorine is in the third period, it can expand its octet. So how many lone pairs are around the central atom? 2. It's not asking for electrons, it's asking for lone pairs. A lone pair counts as 2 atoms. This is a lone pair, and this is a lone pair. Yep. The formal charge would be messed up there. So if we calculate the formal charge of fluorine with a single bond, what are the valence electrons of fluorine? 7. How many lines does it have? How many dots does it have? 6. So what's the formal charge of fluorine? 0, right? So it's happy at 0. If we were to throw a double bond on there, then formal charge of fluorine would then be 7 minus 2 plus 6. And formal charge of fluorine would be minus 1. It's not terrible to be minus 1, but it prefers to be 0. Pretty much never.
Why would you double bond? Because when you're put like an extra pair of electrons on something.
Right. So you could, instead of doing the electrons as lone pairs, right, we're saying, right, do this instead. Right, that then uses those 4 electrons, but now we've created 5 bonds, right, 5
Yeah.
things to fluorine. And then that throws off the formal charge for chlorine as well. Yeah. Yes, yep.
I'm sorry, just right how to do letter B.
Yep. Is everyone okay with question 19? Yep. So for both of these here, so whenever you see something that's a condensed molecular formula, or you see like Cl2, CCCl2, your carbons are usually going to be your central atom. So you want to take your carbons and you want to say, okay, this is what carbon is bonded to carbon. And if you see Cl2 and then a carbon, that means that there's 2 Cl molecules attached to that carbon molecule. That happens on both sides. Then you want to look, right? I haven't even counted the valence electrons. You then want to look at how you're bonding all of your elements. Does carbon have a full valence shell? No. So how do we create a full valence shell? A double bond. So this one would be a double bond. That helps it out. You could then count the valence electrons and you will see that all of these yes, but when we're looking at the way that this molecule is written out just as a condensed form, you could write out the skeletal structure first and then say, I don't have enough bonds right now to carbon, so it's going to create a double bond. And again, 9 times out of almost like I would say 99 times out of 100, carbon will have 4 bonds and no lone pairs because it likes to have 4 valence electrons, right? And that the best way to get a formal charge of 0 is with 4 bonds. Yep. I do believe, I think it's D.
Oh, yeah, that's right.
Yeah, D should be. So your CO3 2 minus we just did. This is CCl2. This is this. This is yeah, so something like that. Or no.
Because I was trying to.
I would have to look at that one a little bit more, but that one should be linear and not the correct answer. Yeah. Mhm. Okay. Let me pull up the periodic table. Okay, so when we look at cobalt on the periodic table, this is element number 27. So when we look at the ground state configuration for just cobalt, not the ion, this is 4s2, 3d, 3d7.
That's another way to write it.
Yeah, it's just putting the lower energy level first. I'm just following the periodic table. So that's ground state. This is for cobalt. Ground state for cobalt 3+ means that we're gaining or losing electrons. We're losing electrons. So cobalt 3+, where is that gonna take away from first? Yep, it's gonna take away from the 4s, which then means that we're going to get rid of one more electron from the 3d. So we end up with 3d6. Yep.
How do you know? Whenever you write down the big electron, sometimes it says for us one and like 3D whatever automatically, like how do you know when you?
Yep, so for your exceptions, it's going to be anything chromium and below that in the same group, and then copper and anything under that in the same group. So when we look at the ground state of copper, it is argon and then 4s2, 3d4. Right, 1, 2, 3. Yep, 3d4. However, this means that we have a 4s that has a paired electron and then a 3d that has 4 unpaired and then 1 empty orbital. And so it's actually energy efficient to jump this paired electron up into this unoccupied orbital. So it's actually going to be 4s1, 3d5. Yes. Yep. And so copper is the same thing here, where this is 4s2, 3d9. So it's more energy efficient to put the paired s electron up into the paired, to make it a paired 3d, right? So it's actually energy efficient to jump this up here and create a full completed 3D or subshell.
So it's not like a D orbital, but it's still over S 15.
No.
Or the-
Nope. So it only happens in the 3D subshell, or it only happens in this D subshell, and it's only for things that are chromium and everything underneath that, and then copper and everything underneath that.
If that's the ground state, it's not the exact state, so.
Yep. So for this is the ground state only for chromium and everything underneath, and only for copper and everything underneath. Yep. So an excited state of this would be something that's like, right, right, this is what chromium is going to look like as the ground state. So excited state right, could have something that's from the 4s orbital jump up to the 4p orbital instead, right? So that sits as the ground state as the lowest energy. The excited state is when it goes even higher than that.
It's an excited state.
Mhm. Any other questions on 16 before we move on? Yes, okay.
I'm so confused why it jumped from like why we skipped 4S and go straight to 3D. Shouldn't there at least be one in there? If it's in that balance show, shouldn't it be 4S1?
For the last thing that I drew,
No, just like in Cobalt 3+, I'm just confused why why we skipped the 4S2.
because, so in 3+, we're gonna take away from the 4s first. So, right, we're losing 3 electrons when we,
Why isn't that the first, isn't the 3D orbital on the 4?
yeah, so when you're removing your valence electrons, you take it from the highest energy level first.
Yeah, but isn't 3, sorry, I thought 3D was the highest.
Highest energy level in terms of number. So number, yes, yep, yep.
So just to clarify what you're saying, so the only exceptions for like you said, say versus ground state, like all transition metals are still going from the asphalt, right, no matter what.
Yes, yep,
Okay, and then you're just saying for the ground state for those two columns that have chromium. Let's see.
Copper, yep.
That is, you're still pulling, that's what will keep it.
yes, yep, yep. So you always, it'll never happen where like something is going to fill the p orbital from the s orbital, but it will happen when something will fill the d orbital from the s orbital. And it only happens with chromium and copper and everything underneath. Yep.
So how do you know when
So your default should be ground state. The only time you want to use the excited state is if they say what's a possible excited state electron configuration, right? They would ask you for the excited state. Yep. Anything else with 16? Yeah. Okay. Yep. So if we're looking at the cobalt ion, right, we just kind of did this. We said that the ground state is going to be four s2 3d7. So you want something that's going to be higher than 4s2 3d7. But in an excited state just means that we're taking an electron we already have and putting it to a higher energy level. We're not removing an electron, we're not gaining an electron, we're just taking the electrons we have and making it into a higher energy level. So how many total electrons do we have outside of the argon? We have 9 total electrons. How many total electrons does A have? How many total electrons does B have? How many total electrons does C have? How many does D have? 7. How many does E have? 9. So what can you remove right away? A, B, and D, right? An excited state means we have the same number of electrons, just at a higher energy level. What is E? E is ground state, so that can be removed right away, and you have C. And if we look at this to confirm our answer, right, we're taking an electron from a lower energy level of S and bumping it up to a higher energy level of the D orbital.
Say that in space.
For removing valence electrons, you look at the numbers. For excited state, you want like energy.
Is there a reason why the question wrote it for D first?
They're just putting the lower number first. Yep. Yep. So for question 12, we said if the electron could have a third spin state that is half, minus 1/2, and 0, what would be the ground state electron configuration of carbon? So you can kind of see what I wrote here. So in the green, we have the original, what is actually happening, an upspin and a downspin for the s orbital. So you can have 2 electrons, one with an upspin, one with a downspin. In our new electron configuration, we now have an s orbital that can have an upspin, a downspin, and then no spin. So that's still counting for 3 electrons, okay? Now S can hold 3 electrons instead of 2. So in our original, carbon is 1s2, 2s2, 2p2. But now we can fill 3 electrons in the s orbital now. So one of these electrons is going to pop into the s orbital, and that creates one s3. And then we would have 2 s1 left over, and that means that those 2 electrons from the p orbital can now pop into the s orbital from the 2p subshell. So that's going to be 1s2, 2s3, right? We still have 6 total electrons within our electron configuration, but now 3 of them are in the s and 3 of them are in the 1s and 3 of them are in the 2s. Does that make sense? Adding them. So we're now saying, right, we can only, in the s orbital, how we know it, we only have a -1/2 and a +1/2 spin. So every time we have a box, no matter if it's s, p, d, or f orbital, we can only have 2 spins at a time, right? Right, so that's what our convention is right now. But now we have a version where we can fill 3 electrons within our orbital. So now we can have an up spin, a down spin, and then a no spin. Right, and now we filled it up. And we're not going to go to a higher energy level until we fill up our entire lower energy level first. So we've used 3 electrons there, and now we're going to fill in our next one. We'll have an up spin, a down spin, and a no spin. Carbon only has 6 electrons. So by the time we get to the 2s and we use all 3 spins that are now available to us, we're done. We can't move on anymore. So now we can have 1s3, 2s3. Yep. Yep. Any other questions on 12? Does that make sense of how we're filling that up? For 14, we have the change in energy for which of the following processes corresponds to the first ionization energy of beryllium. So what does it mean to have an ionization energy? What are we doing? We're removing an electron. So is an electron going to be a reactant or a product in this case? It'll be a product, right? So which one can we remove right off the bat? We can remove E. When we have the first ionization energy, how many electrons are we removing? Just 1. So what else can we remove? D. Yep. We're not going to produce 2 electrons with the first ionization energy. We only produce 1. What is the next thing we need to look at or we need to know about beryllium? This state, right? What is beryllium? It's a metal. What are metals usually? Solid. So which one can we remove? We can remove A, and then what's different about C? Right? C, it changes the phase, right? We have this gaseous phase as our product. That's not going to happen. The only thing that's going to happen with first ionization energy is we're removing an electron. That's crazy. It does have to be a gas, doesn't it? Yeah. Okay. So anyways, C, sorry, it's a Wednesday. C is not going to work because we don't phase change. And then it has to be a gas in order to be a first ionization energy. So even though beryllium is a solid, it cannot remove an electron as a solid. You have to heat it up to the gaseous phase and have enough energy to then remove it from the gaseous phase. So it is A. I apologize for that. Yeah.
That's the opposite of ionization. Where you're getting it from.
Electron affinity. Yes. Yep. Yep. Any other questions on 14? Yeah. Yes, ionization energy, it has to be a gas in order to remove the electron. Okay, what'd you say? 11? 27. Okay, great question. Alrighty, so for 27, we have which of the following substances has the weakest intermolecular forces? Okay. What can we remove right away, probably? Why D? Good, hydrogen bonding. So for D, we have that OH at the end. What are our criteria for hydrogen bonding? Right, in order to have hydrogen bonding, the fluorine, oxygen, or nitrogen must be directly attached to that hydrogen molecule. And in that case, you have an OH that's gonna have the ability to hydrogen bond. That's going to increase our intermolecular forces a ton. So that is incorrect. Okay, what else do we need to know? Yep, so the next thing we need to know is, are they polar or are they non-polar? So when we look at I2, right, we have what kind of polarity? Non-polar. CH18. Yep, this is gonna be non-polar. What does SiH4 look like? Yep. And then what about SbCl3? Okay. I don't know if there's lone pairs on this or not. But I don't even know where Sb is on the periodic table. Sb is 3, 5, 26. Okay, yep. So Sb does have a lone pair on the Sb. So what does that make it? This is polar. Okay. So what can we remove next? We can remove E, right? What kind of bonds or what kind of intermolecular forces is E gonna have? This will have dipole-dipole. So what's left is I2, C8H10, and SiH4. Those are all nonpolar. What are the only intermolecular forces working here? London dispersion forces. What do we have to look at now that we've narrowed it down to just the nonpolar? Molecular weight, right? The greater the molecular weight, the more electrons that are going to be within that system, the greater the polarity difference can be if all of those electrons happen to be on one side of the molecule at a time. Which one? So do we want a high molecular weight or a low molecular weight? We want a low molecular weight because we're looking for the weakest interactions. Which one's our lowest molecular weight? C. Yep. Any questions on 27? It's a way to check your answer. I do believe that this is like SbCl3 is a pretty freaking big molecule. That's going to have pretty strong forces no matter what. So the smallest one here is also your weakest. Yep. Okay, so we're gonna do the molecular geometry for BrO3 minus. What do we see about the minus? What do we have to do? Add an electron, right? So we have bromine has 7, oxygen times 3 has 18. Do mental math. So we have, and then plus 1. We have 26 total valence electrons. What goes in the center? Bromine. We're going to make 3 bonds to oxygen. How many electrons did we use here? 6. So we have 20 left over. Where did those go? Around the O's. How many did we use there? 18. What happens next? We have 2 left. Where does that go? On the bromine. What do we have to check now?
First select.
Oh, double check what you have to find for.
Yeah, double check we've made sure that we have the correct Lewis structure, and that if you need to change the Lewis structure, that doesn't change anything else about your molecule. This does happen to be yeah. Yeah. So in this case, when bromine has 2 double bonds and a lone pair, that creates a formal charge of 0 for the oxygen, bromine, oxygen, and then the oxygen that's a single bond is -1. That matches the charge for your overall molecule. It'll get you the correct answer here, but if you needed to draw the best Lewis structure, the oxygen with the double bonds are correct. Yes. Yep. So in this case, we have -1, -1, -1, and then +2. So they all have formal charges and none of them are 0. Yep.
On some of your practice problems that you posted, like whenever you're comparing bond lengths from longest to shortest, like based on negativity that you have two that are really similar, how do you know what?
Yep. So I'll go to that in 1 second. I'm just going to finish this question. So no matter what Lewis structure you drew here, what is your electron domain geometry? Tetrahedral. Right? We have 4 electron domains, 3 from bonds, 1 from the lone pair. What is your molecular domain geometry then? Trigonal pyramidal. And that's going to be E. Does that help your question? So your question. Yep.
Those, like, if you guys check the total charges, then that would pretty much work.
Yeah.
Okay.
Yep. Alrighty, so we're looking at bond length from longest to shortest. So when you're comparing something that are very similar in electronegativities, we still need to look at the trend for electronegativity and for atomic radius, right? Bond length as a definition is the length between the nuclei of your 2 atoms that are being bonded. So here, all of them are being bonded to carbon. When we look at bromine, chlorine, and fluorine just by itself, where are those on the periodic table? Those are all halogens. They're all going down the group. As we go down the periodic table, what happens to atomic radius? Atomic radius is going to increase. So which one is our largest out of bromine, chlorine, and fluorine? Bromine's our largest, so we think bromine, then chlorine, then fluorine in terms of, right, big to small. We then have to look at oxygen and nitrogen. What happens as we go across the periodic table? And fluorine. Yep, atomic radius is going to decrease. So when we look at big to small here, we have nitrogen and then oxygen and then fluorine. What's the difference between chlorine and oxygen? They're both directly next to fluorine, but what's the main difference between the two? Chlorine's bigger, right? It's in another period. It has a whole other valence shell in comparison to oxygen. So even though they're both relatively similar in electronegativities, the chlorine molecule has a giant extra valence shell compared to the oxygen. So your bromine and chlorine, since they are lower on the periodic table, are going to be your larger ones, and then you compare your ones going across. No matter what, fluorine's the smallest. Yep, so in terms of atomic radius, going down the periodic table is going to have more of an effect than going across. Yep, so bromine and chlorine are going to be your biggest because they're in period 4 and then period 3. Nitrogen, oxygen, and fluorine are all in period 2, so you compare those together as well.
The element of bond or the bond.
Yes, right, because it has, right, you're comparing 2 valence compared to 3 compared to 4, right? So the distance from the nuclei of both of those are going to be small. It's going to be larger. It does, but not as much as atomic radius. The chlorine has a longer bond because it has a whole extra valence shell.
That makes sense.
Yep.
So the carbon
The carbon fluorine would be, the carbon would be in between the chlorine and the nitrogen. Because your carbon is more left on your periodic table compared to your nitrogen. And the atomic radius decreases as you go across. So carbon's going to be bigger than nitrogen, which will be bigger than oxygen, which is bigger than fluorine. Does that make sense?
You're not really looking at like.
Nope,
Just.
just atomic radius. Yep. Yes. So fluorine's your smallest element out of bromine, fluorine, carbon, oxygen, and nitrogen. Or sorry, bromine, fluorine, chlorine, oxygen, and nitrogen. So the distance between carbon, because that's all staying the same, and the smallest element is going to be the smallest. On my extra problems? Yes. Okay, do you have a question? Yep. So for question 4, we're ranking ionization energy here. What do we need to remember about ionization energy going across a period? It increases, but it also decreases a little bit, right? So the one, once you fill a valence or once you fill an orbital, the next one is going to decrease in ionization energy a little bit. So if we just compare, right, if we look at going across the periodic table, we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay. Ionization energy is similar to atomic radius, where it depends more on where it is on the periodic table going down, right? The larger the element, the bigger the effect on ionization energy it'll have first before going across. So looking at what I've given you, you want to rank everything in period 3 first. When we go from sodium, which has 1 unpaired electron, to magnesium, we have a paired electron in the s orbital. It's going to be hard to remove that paired electron. It wants to remove the 2 of them, but it's going to be pretty hard to do that. When we go to aluminum, we have a paired electron in the s orbital and then an unpaired in the p. It's going to be easier to remove that unpaired electron in the p orbital than to remove the paired electron in the s orbital, right? It's a little bit closer to the nucleus as the s orbital, and then the p orbital is a little bit farther away. So it's easier to pick that one off. So this one is actually easier than the magnesium. So that's why sodium is first, because that's number 1 in the on the row, and then aluminum, and then magnesium. Silicon now has, right, 2 unpaired. So it gets a little bit harder now. I forgot to include phosphorus, but that would be the next one. Sulfur will then decrease, right? So phosphorus would be high, then sulfur would drop back down low, but not as low as silicon. And then chlorine, because that's going to round out the period, or that's going to round out the period. We then are left with fluorine and neon. Fluorine is above chlorine. It's a little bit smaller. It's going to be harder to remove that electron from the smaller atom compared to the larger ones. That's what's next. And then neon has a full octet, and so it's going to be really hard to remove electrons from there. Does that help?
What is exactly like, what is it for its kind of the ionization? What, in what sense do you need to know?
You'll talk about like energies later on in the semester a little bit where it might come into play, but it's just more of a trend of knowing electron configurations now. Yeah. Yep. On me. Yeah. So this is just in case they throw a wild card at you. So B is EU. This is actually going to be in the F block. So you're going to follow the periodic table the same way that you would follow anything for the 4S and 3D. But when you jump down to the F block, you are now 2 periods or 2 energy levels behind the period that it's in. So 6s2 starts off that period, and then you have to go down to that first energy block or that first row in the F block. And that's going to, excuse me, be the 4s orbital. So you're going to fill that one first.
Like the X. Okay.
Yep, and then you would have xenon. Electron, it can have 14. Yep, you have, right, because the first time if L is equal to 3, right, that's the first time you see F. Then M sub L can equal -3, -2, -1, 0, 1, 2, 3. And there's 7 options there that can each have 2 electrons, so 14 total. And then if you count the F block, there's 14 elements in there. Yep. So I might have messed this up this morning. So when you're looking at orbitals is determined by Eb sub L. So when we have subshells for L, the number of subshells or the subshells available are S, P, and D, right? So that's going to be 0, 1, and 2. If you have L is equal to 2, that means that M sub L is equal to -2, -1, 0, 1, or 2. So there's 5 orbitals that you can fill for L. M sub L, when L is equal to 1, M sub L can equal -1, 0, 1. 3 options there. And then L equal to 0 means that M sub L is equal to 0 as well. There's only 1 option there. So that's where the 9 orbitals come from. How many electrons can I have? 18, great. Yes, yep, so the subshell is SPDF, orbital is the orientation of where it is. So subshell is determined by L, orbital is determined by M sub L. Yep. I don't remember for Bengali what he said it was gonna be up to, but we can go over it. Okay, I think that's on yours. So when we talk about vapor pressure and boiling point, really for Altimos, what you need to know is the concepts behind these. So, right, and this has to deal with intermolecular forces. So if we have high intermolecular forces, what does that do to our compound? Does it keep it close together? Is it able to break apart? It keeps it close together, right? So high intermolecular forces means that it acts more solid-like, if you want to say. So if you have something that's starting at a solid, what do you need to do in order to make it a gas? you need to put a lot of energy into it. You need to heat it up. So if you have high intermolecular forces, that means you're going to have a high boiling point. If you have a high boiling point, what does that mean for your vapor pressure? That's going to be low, right? Because if it can't escape into the gaseous phase, it can't have pressure from your vapors. That means that you have a low vapor pressure. So inversely, right, if you have low IMFs, you have a low boiling point and you have a high vapor pressure. Right, think about like dry ice, right? That boils very quickly, or liquid nitrogen. Liquid nitrogen is a good one, right? That boils under very low temperatures. So you can see if someone pours that into a dewar in class, it's going to boil, right? It can quickly escape to the gaseous phase and you see the vapors come off pretty easily. But if you poured water into a container, right, that's going to stay as water. It has a high boiling point because those intermolecular forces are much stronger than liquid nitrogen. Yep, so if you're looking at molecular weights of things, within 30 grams per mole of your molecular weight, then the weight doesn't matter, right? You have to look more at the intermolecular forces between polarity or hydrogen bonds. Anything greater than 30 grams per mole, then you can say, okay, the weight of this is going to have more of effect than anything else. So, like in terms of vapor pressure and boiling point? Yeah. Yep.
I remember sharing something about the weight during the part here.
Yep. So similar to the question we did. Was it 27? We were looking at. Yeah, 27 here with like the weakest intermolecular forces. So your D here with hydrogen bonds, that is going to be your highest because that has the strongest intermolecular force. And so that's going to have, since that one has hydrogen bonds, that one's going to have the highest boiling point here. Your SbCl3, that one is a polar molecule, it has dipole-dipole. So now you're going to say, okay, that's going to have a greater effect than anything that has just London dispersion forces. Then comparing the three that are nonpolar, now you look at weight and you say, okay, all of these intermolecular forces are the same. They only have London dispersion. How heavy is the molecule? And that creates stronger weak intermolecular forces. So in this case, the SiH4 is the smallest molecule. It'll have the weakest intermolecular forces. So it'll have the lowest boiling point and the highest vapor pressure. Mm-hmm. Yep, so for number 10, we're just asking the hybridizations of the following structures. So when you look at hybridization, you just want to look at how many electron domains are on that central atom. So for CH2O here, how many electron domains are there around that carbon? There's 3 electron domains. That means we need 3 orbitals in order to create a hybrid orbital. The first one will always be S, and then you have 3 p orbitals to choose from. You only need 2 out of the 3 to create 3 total orbitals, right? If you were to combine the exponents from S and P, that equals 3. That matches your 3 electron domains. Okay, how many electron domains are on B? 4. So how many orbitals do you need? 4. So that's going to be the S and then 3p. Okay. And then same for carbon dioxide. There's only 2 electron domains. You only need 2 orbitals, and that's going to be the sp orbitals. The highest you would get is sp3d2, and that's with 6 electron domains. So just octahedral. Can you have 4p orbitals? No, right? So if you need a fifth orbital, you need to go to the D. What is hybridization? So it's instead of having an s orbital here and p orbitals here and the difference between them, they kind of average them out and they create this in-between one that's at a lower state than if they were at an s and a p. Now you're at an SP and it's somewhere in the middle. Yeah, I don't think for you it is. Yeah.
I'm so confused.
I don't think he ever did. I can't remember though, so. Yeah. Yeah. SP3D2. So highest is SP3D2, and that's 6 total orbitals for 6 total electron domains. Well, you tell me, what would 5 be? SP. Yep.
And just really quick, explain whether silicon or arsenic have like a smaller radius.
Yes.
Use the over it.
Yep. So silicone is in period 3, and then arsenic is in period 4. So which one's going to be bigger?
Oh, like just in general.
Just in general, arsenic is going to be bigger. Yep. Questions? Yep.
About exceptions, just.
Yeah.
Guess kind of like the fear of trend.
Yep.
Exceptions.
So your exceptions are going to be ionization energy. And I want you to remember that graph where it goes up, then down, then up, then down, then up. And this is 1, 2, 3, 4, 5, 6, 7, 8. Not including transition elements, right? Just the S and the P orbitals, or S and P blocks. Beryllium can only have 4 total electrons, 2 bonds usually, and it's happy with its octet. Boron can have 6 total electrons, which is 3 bonds. Excuse me, thank you. Period 3 and below can expand its octet. Can anyone think of any other exceptions? I think these are the big ones. Yeah, aluminum is the same. That one can have 3 as well, right? Beryllium, or sorry, boron is in the same group as aluminum, so anything under boron also follows that rule. Yep, great. Chromium. Ground state. Electron configuration is 4s1 3d5. And then copper ground state electron configuration is 4s1 3d10. And that applies to anything underneath both of those elements. So anything in the same group.
So basically, like beryllium and boron, it's the same thing as that, like anything in the same group as that, the rules still apply.
Yep.
So for those ones where the ground state electron configuration is different.
Yep.
Whenever one of them gets excited, like how do you know where they go? So they can be on over those valves. So
Yep, so it doesn't, it'll probably come from the d orbital and it will stay like a 4s1, 3d4, 4p1, right? So this would turn into right, it can jump up from the d orbital to the p orbital. So it's still the same number of electrons. We still have 6 total electrons, but we've now taken one from a lower energy level, or a lower orbital and put it into a higher orbital.
Like C plus where it's like other electrons.
It'll remove it from the s orbital. When you're removing a valence electrons, you want to take it from the highest number energy level first. So 4 is greater than 3, you're going to take from the s first. Nope, you're always going to jump up. No. Not that you need to worry about, at least. Yep. From Bengali. Oh yeah, great question. Okay, so for question 6, we have what is the wavelength of an electron traveling at 3.74% of the speed of light? So some things you need to look at here is that, right, you're given the mass of an electron, you're given Planck's constant, and you're given the speed of light. When we look at, the wavelength of an electron and you're given a mass, what should that indicate for you to solve for? De Broglie wavelength, yep. So when we have a de Broglie wavelength, that takes into account Planck's constant, the mass, and the velocity. It is given to you, yep, but you just need to know to use it here, right? It's not saying solve for the de Broglie wavelength, but you're given a mass, and so that indicates de Broglie wavelength.
But on your review questions, can you do number 6?
Yep, let me finish this question first. So when we have the de Broglie wavelength, we're given h is a constant, so we're solving for the wavelength, that's lambda. We're given 6.626 times 10 to the negative 34. We're given a mass, that's the mass of the electron. And how do we find the velocity? Yep, we need to take the percentage and multiply it by the speed of light. I don't remember what that is. So that's going to be 1.122 times 10 to the 7th meters per second. And then you can plug in chug from there.
C is the speed of light.
C is the speed of light, yep. So that's this constant here given. Any questions from there? You said 6 from mine? Yep, so when we were looking at 6, we said when n is 3 and L is equal to 2, how many electrons are in the subshell? And then give an example of the potential quantum number. So the subshell here is indicated by the letter L. So we're saying that we know that n has to equal 3, all right, we have NL, n sub L, and n sub S. So we know that L has to be, or we know that n has to be 3, and we know that L has to be 2. Okay. So if L is equal to 2, what are the options for m sub L? Right, we have 5 options for m sub L. So if there's 5 options for the orbitals, how many total electrons can we have? We can have 10 total electrons. So that's where this 10 comes from. And then I gave the options, right? You have -2, -1, 0, 1, and 2. And then you have plus or minus 1/2 for each of those orbitals that you're in. So I wrote 5 options with plus or minus, give you all 10 options for the quantum number.
So how sometimes people say that like L could be 0, 1, and 2.
So when we say for 7, right, we're saying the only thing that's defined is n is equal to 3. So the options that we don't know is anything that follows it. I've restricted you to just L is equal to 2 in 6. Yep. Okay, great. So we have here, which element or ion listed below has an electron configuration of 1s2, 2s2, 2p6. So when we have 1s2, 2s2, 2p6, we can follow the periodic table to find out what element that looks like. Does anyone know what this one is? This is neon. Okay. If we were to write out the electron configurations for the ground state of sodium, it would be neon 1s1. This would be calcium is argon 1s2, and chlorine is is neon Good Lord, sorry. This is not good. This is 3s1. This is 4s2. And this is 3s2. Okay. That's for the ground state of all of these. For sodium plus, are we removing or gaining an electron? We're removing. So what does this turn into? Just neon. For calcium 2 plus, are we gaining or removing an electron? We're removing how many? 2. So what does this turn into? Argon. And for chlorine minus, are we gaining or losing an electron? We're gaining. So what does it turn into? Yep, it would be neon 3s2, 3p8, which is now equivalent to argon. So which one matches neon? A. Oh, I'm sorry. I'm thinking 8 valence electrons. Sorry. Yep. Mhm. Yep. So when we're looking at diamagnetic, what does it mean to be diamagnetic? Yep, this means all electrons are paired. When we look at vandanium, this is going to be 4s2, 3d3. Does that have paired or unpaired electrons? That's unpaired. Nickel is 4s2, 3d8. Is that paired or unpaired? We have some paired, some unpaired, but we do have some unpaired, right? In order to be diamagnetic, it needs to have all paired electrons. So that one doesn't count. For zinc, we have 4s2, 3d10. What is that one? That's all paired. That one's diamagnetic. Fluorine is 2s2, 2p5. What is that? One unpaired, can't be diamagnetic. Neon is 2s2, 2p6. What about that? All paired. Magnesium is just 3s2. That's all paired. Gold is 4s1, 3d10. We still have that unpaired one from our 4s orbitals. That one's going to be paramagnetic. Barely, but it is. And then krypton is a noble gas. And so what is that one? That's all paired, so that one counts there.
The subshells are half.
Yes.
Sorry, I should have asked when you run the other practice test. On the previous one that we were just on, can you go over question 2 on that?
Any other questions on 3? Yes, and I'm sorry, I meant to put magnesium there. Yeah. That's why I circle all of them as well. Yeah. You said 2? Yeah. So here we have which of the following atoms is paramagnetic in the ground state. So radon is a noble gas. So what is that one going to be? This is diamagnetic. Sodium we said is 1s1. What is that one? Probably paramagnetic. Barium is 6s2. What is that one? That's diamagnetic. And then mercury is 4s2, not 4s. 6s2, 5d10. That one's also diamagnetic, so B for that.
Sorry, with like the diamagnetic, what's so with like gold, and like copper and all those, because even though if we didn't remember, we said that like, oh, 5s2, 4d9, that's still not all.
Yes.
Would cover the-
Yes. Yep. Yeah. Briefly.
Sorry, I'm just.
Yeah. Compare each of them separately. Yeah, so like the central atom to the 2 terminal atoms. Yes, yeah. Yep.
And then also, once it has like a subgroup that goes is the subgroup for forms of site electrons, or you just look at certain things?
Just look at how each of them are compared to that central atom, right? So if it's CH4, that means that carbon's going to be attached to 4 hydrogens. So individually look at each of those electronegativities between the carbon and hydrogen. Those would all be nonpolar, so you're covered. No, you just need to know that an s orbital is spherical and then your p orbitals are dumbbell shaped.
Like, you have to look at both them with their body.
No, nope. You just need to know that if in a double bond, you have 1 sigma bond and then a pi bond, and then a triple bond is 1 sigma, 2 pi.
Not related to the chemistry, but one of the quiz
Mhm.
questions.
Yeah, like, some of them is already. Yeah, sorry. I thought
Yeah,
that's-
so that's gonna be. I think there was one of them on your exam on Bengali. It's on Ultimo, so
Okay.
excuse me, sorry.
There you go.
So when you're, I'll kind of go over that. So that's kind of, I think I did a practice problem on that. Yeah. So when you're looking at transitions between right, when you're looking at this transition here, the transition from 1 to 2 and 2 to 3. So E2 to 1 plus E2 to 3 is going to be equal to E3 to 1.
I have.
Yep, so then all of these can be HC divided by lambda. So then all the HCs cancel out, so you're just left with 1 over lambda plus 1 over lambda. Yes. Yep. Thank y'all. It'll be fine. There's leeway. Leeway, you're good. Yep. Yep. Yeah, there's a little bit of tolerance there. Yep. Okay. Yep. Yeah, stuff like that. Where transface transitions are and all that fun stuff there. Okay, I think that's a good spot to end. Yeah.
Slide on those. How to calculate the energy of a it'll like random formula. We need to know that.
Now you don't need that. Okay. Okay, we'll end it there and I'll see you tomorrow or Friday. Yeah, please come take candy.